Hello! Welcome to this course, IC Design Process, a beginner's overview to VLSI technology. This course is presented by Systemverilog Academy. It is an online platform to learn Systemverilog hardware description language for both design and verification coding. Visit us at systemverilogacademy.com for in-depth Systemverilog trainings in all levels of expertness, beginner, intermediate, or advanced. This is a beginner-level course. When anybody start learning a hardware description language, such as Systemverilog or VHDL, the most common problem they could face is in connecting what they write in their program to the actual circuit that get produced in the silicon. This is a course designed to simplify this problem by connecting together the pieces of information scattered throughout RTL design, functional verification, synthesis, physical design, and manufacturing in VLSI technology. This is not teaching any specific hardware description language or anything related to coding in an HDL. Course Overview. As this course is teaching more theory than coding practices, it is designed to be a short one and gives only the overview of every process. The first session explains a short history of ICs. Second session refreshes few fundamentals of digital circuits. Third session describes the idea of hardware description language. Fourth session gives the overview of every steps involved in the design process of an IC. It is broadly classified as front-end and back-end design processes. Fifth session briefs the IC manufacturing process, and the final session summaries the course. History of ICs. An integrated circuit, or IC, is a device with a large number of electronic circuits built into a tiny plate of semiconductor material, which will be usually silicon. An SoC, or System on Chip, is an IC with all components of a complete electronic system built into a single silicon plate. Or simply, an SoC is a device with multiple ICs built in a single chip. Even though the actual silicon in an IC is a tiny metal piece, they could be built with up to several billions of transistors and other electronic components in it. As you know, there are two categories of electronic circuits, analog and digital. In the same manner, ICs can also be analog or digital based on the number of operational voltage levels in them. Design process of analog and digital ICs are not very similar. But the manufacturing process for both of them are almost similar. Usually, HDLs are used to design digital ICs, and this course is explaining the process on the grounds of a digital IC. Every digital circuit is made of switches that turn on and turn off the voltage. Before the invention of BJT, the bipolar junction transistor, circuits were using vacuum tubes as these digital switches. You can imagine how bulky was even a simple laboratory circuit that used vacuum tubes instead of transistors. With the invention of transistors in 1947 at Bell Laboratories, vacuum tubes were replaced by these small silicon devices. But still, the whole circuit was made of discrete transistors. Eventually, the idea came up that proposed to build all transistors and other components in a whole electronic circuit into a single silicon piece, instead of manufacturing them separately and assembling. This was nothing but what we call as an integrated circuit, and from there, IC technology evolution started and made it possible to build up to billions of components into a single wafer. VLSI. The first integrated circuits build only a few devices in them, perhaps as many as 10 diodes, transistors, resistors, and capacitors, making it possible to fabricate one or two logic gates on a single IC. This number started to increase slowly and gone up to billion in 2008. Based on the number of transistors made into a single chip, The manufacturing technologies were known by different names in the industry, like SSI or LSI. Early in the 1960s, hundreds of transistors were built into a single chip, and technology was commonly known as SSI, or small-scale integration. It went up to thousands of transistors in late 1960s, which was known as medium-scale integration, MSI. In 70s, it increased to tens of thousands of transistors, and the technology was known as large-scale integration, or LSI. Eventually, the number of transistors in a single chip increased to hundreds of thousands of transistors in the 1980s, millions in late 90s, and to billions in 2008. Nowadays, irrespective of the number of transistors in the chip, all IC manufacturing technologies are called by the same name, VLSI, or Very Large Scale Integration. Fundamentals of digital circuits. Before you start designing digital ICs, there are a few fundamentals of digital circuits that need to be refreshed. In digital circuits, all real-world entities, that is the data, will be converted to binary numbers using mathematical formulas, as a 1 can be represented with a positive voltage and a 0 with negative voltage. The only requirement to process this binary data in the circuit is to switch on and switch off the voltage in the circuit. Thus, we can say that switches are the basic building blocks of any digital circuit. Normally, transistor and CMOS devices are used as these switches. There are two types of digital circuits, sequential and combinational circuits. A digital circuit whose output depends not only on the present value of its inputs, but on the sequence of past inputs or the input history, is called a sequential circuit. On the other hand, a circuit whose output is a pure function of only its current inputs is called a combinational circuit. In simple words, a digital circuit with a memory storage element in it will be a sequential circuit, and without memory will be a combinational circuit. Once you have written the state of any digital circuit and simplify it using the mathematical formulas, there will be only two types of components in it, which are the logic gates and flip-flops. As you know, there are only 7 logic gates whose symbolic representation is shown here. They are the AND, OR, XOR, NOT, NAND, NOR, and XNOR gates. A flip-flop is the memory storage element which can store a single-bit input data in it for the duration of a clock signal. All types of flip-flops like D-flops, JK flops, latches, etc. are again made of logic gates. As an example, this figure shows a D flip-flop made using logic gates. Thus, we can say that every digital circuit is made of only logic gates. This breakdown will further go down into transistors, as all logic gates can be made with only transistors. Here is a diagram representing a NAND gate and NOR gate using CMOS transistors. Thus, every digital circuit is made of gates and flops. Flops are made of gates, and all gates are made using transistor. This concludes that every digital circuit is made of only with a large number of transistors. To simplify the design process, our aim is to model the complex digital circuits in an abstract way, which hides details of its transistor-level circuit diagram. This is the whole purpose of using a hardware description language in IC design. Hardware description language. As you learned in the previous session, in early 60s itself, the number of transistors in a digital circuit have gone beyond the point where it was possible to draw as a transistor-level circuit and make a mask for the fabrication process. Thus, it became essential to describe the circuit behavior in a high-level manner, which is independent of any library or technology that is used in the manufacturing process of the IC, and uses EDA tools to convert the written program to a mask diagram used in the fabrication process. This programming language is called as a hardware description language, or an HDL. A few years ago, Verilog and VHDL were the most common HDLs in the industry, and nowadays, Systemverilog, which is an extension of Verilog, is the widely accepted language by most of the semiconductor companies. Verilog language. Verilog was developed by the company Gateway Design in 1984, which was later acquired by Cadence Design Systems. It got its name from the words verification and logic, and became an IEEE standard in 1995 as IEEE 1364. The Verilog HDL is now maintained by a non-profitable organization called Accelera. Systemverilog HDL. Systemverilog is an extension of Verilog and was developed by Accelera as a new standard. It became an IEEE standard in 2005, which is IEEE 1800 to 2005. Compared to Verilog, Systemverilog added a lot of features to support functional verification of the IC. Out of these, support for object-oriented programming was a significant add-on, which helped it to become the most preferred HDL in the industry, as it can be used for both design as well as verification. When you write a design code in Verilog and Systemverilog, they look almost the same. But in case of a test bench or verification code, Systemverilog is much more advanced than Verilog. IC design and manufacturing process. The process of making an ICs can be broadly classified into two: in need to design first and manufactured next. The design process is subdivided into front-end and back-end process, which consists of specification, design, verification, synthesis, and physical design. Each of these design and manufacturing process contains many sub-phases in them, which are explained in the upcoming sessions. IC design process. In this session, you will quickly go through the complete design process of an IC. The first step is to decide the functionality of the IC. Here, the specification of the IC is written, and its microarchitecture is defined. In the next phase, these specifications will be programmed in a hardware description language like Systemverilog. This is called the RTL design phase of the process, and writing Systemverilog code is often referred to as the RTL code, where RTL stands for Registered Transfer Layer. The next phase is functional verification. Here, the design is simulated using extra piece of Systemverilog code called as the test bench or TB code. The test bench will use a simulation EDA tool to inject stimulus into the inputs of the design and will check the correctness of its outputs. This will expose the issues or bugs in the design, which will be fixed in the RTL code. These phases are repeated multiple times until the RTL code is bug-free. In the function verification phase, apart from checking the correctness of the RTL, the quality and completeness of the testing process will also be ensured by using coverage analysis techniques. The RTL design and functional verification phases are usually called as the front-end phase of IC design process. When the functionality of the IC or SoC is very complex, as in the case of a microprocessor, mobile PCU, or graphics processor. It is impossible completely to do any of the above phases, which are the specification definition, RTL design, and functional verification, by one person or a group of people. It is accomplished by subdividing the whole IC into multiple units. Here, the whole IC, or SoC, will be split into multiple clusters and clusters again into units. Each of these units will perform well-designed functions in their input-output boundaries. The microarchitecture of each unit is defined in the specification phase. Also, RTL design and functional verification are performed in unit-level boundaries. Once the units are stabilized, that is when are bug-free. The functional verification will be done at cluster level and SoC level, which will ideally expose all bugs in the RTL. Those were hidden at unit-level verification. When the functional verification is complete at SoC or IC level, the front-end part of design process is complete and will be sent for back-end process. IC design, the back-end process. Once the verified RTL is ready, the HDL code will be converted to digital circuits with only logic gates and flip-flops. This process is called as synthesis, and it is done by using EDA tools. The output of synthesis will consist of list of logic gates connect appropriately to perform the design functionality of the IC. It is usually called as a net list, and it can be assumed as the circuit diagram of the final IC, with only logic gates in it. This gate-level representation of the circuit need to be converted to a geometric representation of shapes, which, when manufactured in the corresponding layers of materials, will ensure a circuit of transistors doing the intended functionality. This process is called as physical design. In simple words, physical design is the process of generating a photomask, which can be used in the fabrication process to produce a transistor-level circuit of the whole IC in the silicon. The synthesis and the physical design phases are commonly known as the back-end phase of IC design process. Physical design process. There are many details in every phases of physical design, and here it is summarized in a very abstract manner. Synthesis is the process of converting the HDL design code to a gate-level representation of the whole circuit, which is called as a netlist. Next phase is floor planning. Remember from the previous session that in the front-end design phase, the whole IC will be divided into subunits or blocks to make the process easier. In the floor planning phase, you will decide which blocks or subunit will be made in which region of the metal in the final IC. That is, here the whole area of the actual silicon metal is assigned to major blocks or units of the design. This will also fix the position of input and output pins of the IC. Here is a representative floor plan of a design. These rectangles could be major blocks of your design or different IPs purchased for this design. Next phase is placement, which is a highly complex and important phase in back-end design. In simple words, it is the process of assigning location to the gates of the circuit in the silicon, while optimizing a lot of power and performance constraints. It takes many iterative processes to complete this step. Clock insertion phase. Here, clock signal wiring is introduced into the design, which are commonly known as clock trees. Clock signal need to be driven to every part of the circuit, with the capability of gating the clock as and when needed. Clock gating is a process of saving power by shutting down a part of the circuit when it is not active for a small period of time. The clock tree is a metal grid, which distributes the clock signals from a common point to all the elements that need clock, considering the clock gating. Till this point of physical design process, you have decided the position of all blocks in the IC and the position of each logic gate of the circuit in the silicon as well. Obviously, the next step is connect these gates according to the circuit diagram, which is done in the routing phase. Routing, or wire routing, is the process of connecting different components placed in the circuit appropriately using metal wires. To understand placing and routing phases in the process, you can compare them to the same steps in PCB design. In the next phase is design for manufacturability. Here, the design is modified where possible to make it as easy and efficient as possible to produce. This is done by adding extra vias, or adding dummy metal, diffusion, or poly layers wherever possible, while complying to the design rules set by the foundry. Last phase in physical design process is tape-out and mask generation. After doing a lot of iterations in above steps, which at most care, the design data will be ready, and it need to be converted into photomasks in this phase. The final photomask will be generated and sent to the manufacturing foundry to produce the IC on silicon. This is called as tape-out, as magnetic tapes were used to write this photomask in early days. Nowadays, the final photomask will be delivered in GDS2 format. It is a binary file format representing planar geometric shapes, text labels, and other information about the layout in a hierarchical form. The data can be used to reconstruct all or part of the artwork, that to be used in sharing layouts or creating photomasks at the foundry. All the steps in physical design are explained in a very simplified manner here, but remember, in actual exercises, all of them are too complex, costly, and time-consuming. IC manufacturing process. After physical design phase, which will generate the photomask in GDS2 format, the next step is to manufacture the IC in a foundry. Again, there are a lot of steps involved in the manufacturing process, from producing the silicon wafer from sand till packing and testing of the final IC. The most simplified description of IC manufacturing process are given here. First, you need to build transistors on silicon, then connect them according to the circuit functionality, and finally, pack the IC into its case and test it. Building a C-MOS NOT gate in silicon. The transistors used in modern ICs are MOSFETs. They are of two types, PMOS and MMOS transistors. Here, the first diagram shows how an NMOS and PMOS transistors are manufactured into a P-type substrate. The NMOS needs two N+ regions in the P substrate, and PMOS need two P+ regions in an N well. The second diagram shows the circuit diagram of a NOT gate made with a PMOS and NMOS transistors. The third diagram shows the cross-section view of a NOT gate made in a P-type substrate. If you compare the first and third diagram, it shows the drain and source of both transistors are connected together to form a circuit equivalent to the second diagram. Note that the gate, source, and drain contacts are not normally in the same plane in real devices, and this diagram is not to scale as well. To manufacture a complex digital circuit in an IC, the same principles applied as above. That is, first the transistors are made into the silicon, and then they are connected to form the final circuit. There are a lot of complex steps involved in building all the transistors in silicon, which are not explained here. You can imagine that, when you completed the build transistor phase, there will be billions of transistors built into silicon, looking something similar to these diagrams. Next, you need to connect the transistors to form the final circuit. Connecting transistors. In order to connect the billions of transistors according to the circuit diagram, just one layer of connection will not be enough. There will be multiple layers of connecting wires sitting on top of one another, separated by an insulating material. Its cross-section view will look something similar to this diagram. It shows 5 layers of connection between transistors, and there could be up to 9 connection layers in a complex IC nowadays. Here, SOD, or spin-off dielectrics, is a coating material that insulates between transistors or between conducting metal wires. These are the conducting metal connections, and the other end of this metal will be connected to some other transistor sitting in the IC. This 3D diagrams is an animation of connection layers in a small part of IC. Now you can imagine how complex will be the complete connection diagram in a real IC. From these descriptions, it is clear that you need 2 types of database to manufacture and connect transistors. First, the photomask to make billions of transistors in silicon, and second, the connection information between these transistors over multiple layers. These 2 complex requirements are solved in the physical design process and will be available in the GDS2 formatted database. Once the transistors are made and connected to for the final circuit, it will be packed in an insulating material with connections made to external pins. Different kind of testing will be done on the wafer in between these processes and on the final IC at the end of production. All these manufacturing process will take from 1 to 2 months to complete, and finally, the IC will be packed as product and shipped to the market. What you have learned here is a quick overview of the whole IC manufacturing process, and there are a lot of complex procedures in each and every phases of this process. Also, there are a few good YouTube videos that shows their phases in a real IC foundries, which I strongly recommended you to watch, even if you are not planning to learn more about the manufacturing process. Few of the selected YouTube video links are given here for reference. IC Design and Manufacturing Process Summary. Here is a quick summary of the complete process. First, the idea or functionality of the final product is defined as specification. This is coded in an HDL at different subunit level. Then, the code will be verified at unit level, cluster level, and finally at SoC or IC level. These phases are commonly known as front-end design process. The final HDL code is converted to a gate-level circuit using synthesizing tools and will produce a GDS2 formatted photomask that is used to manufacture the IC. These are commonly called as the back-end design process. Once the final photomask is taped out, it will be used to manufacture the IC in a foundry. After production, each IC will be validated and finally shipped as a product to the market. Summary. Here is the summary of the course. Every digital circuit is made of a large number of transistors. You will use a hardware description language to code behavior of the IC and use EDA tools to convert this program into its equivalent transistor circuit. The coding phase is known as the front-end design and other one as the back-end design. Once the transistor circuit is ready, its photomask and connection layers will be generated, and the circuit will be manufactured in silicon. In the manufacturing process, first transistors are built into the IC using photomask, and then they are connected over different connection layers to form the final circuit. This course was offered by Systemverilog Academy, and here you reach the end of the course. Systemverilog Academy is an online learning platform offering different courses in the HDL. This is the first ever course we published, and there are a number of others on the way over the next few months. These will teach Systemverilog for both design and functional verification coding. Apart from the online courses, we have also designed more personalized practicing techniques in Systemverilog, which will make you to code and learn the programming language. These will also be released soon at systemverilogacademy.com. And remember, all of them are prepared by experts from the industry who have extensive work experience in SoC design and verification. Please visit us at systemverilogacademy.com and subscribe to us. We will keep you posted about the release of new courses and practicing session. Also, you could get great offers and discounts as well. Thank you very much for enrolling this course, and we are really happy to see that you have completed successfully. We hope this was informative for you and would really appreciate if you could leave your honest feedback on this course. Don't forget to visit us at systemverilogacademy.com. Thanks again.